So now shifting gears to another type of fuel, this is natural gas. Natural gas is mostly methane, which is CH4, and it produces only half as much CO2 as an equivalent amount of coal. Therefore, it is considered to be quote unquote cleaner burning compared to coal. However, more than half of all the world's proven natural gas reserves are in the Middle East and the former Soviet Union. So as far as domestic production of natural gas, we really don't have a whole lot to talk about here in the United States. The total ultimately recoverable natural gas resources in the world are estimated to be about 10,000 trillion cubic feet, which is a 60-year supply at present usage rates. So here we have the different regions that have proven natural gas reserves. As we just mentioned, the Middle East and Russia take up the lion's share of natural gas or methane, with North America having roughly 5.3% of natural gas. So moving from natural gas to nuclear and hydropower. These are different types of energy sources. And in 1953, President Dwight Eisenhower presented his, quote, Atoms for Peace speech to the United Nations. And there at a meeting at the United Nations in 1953, he announced that the United States would build nuclear-powered electrical generators to provide clean, abundant energy for all of its citizens. So today, in terms of nuclear reactors, there are about 440 reactors in the world in use worldwide, and about 104 of those are in the United States. The Tennessee Valley Authority does rely on nuclear power, as we showed in those pie charts earlier. And about half of the US plants, 52 of them, are more than 30 years old, and thus approaching the end of their expected operational lifetime. So you might be wondering, well, how does this entire process work? I understand how fossil fuels, they're burned for carbon. They've got lots of energy stored in those carbon molecules, but what about nuclear power? So how do nuclear reactors work? There's radioactive uranium atoms that are extremely unstable and represented here. And so when they're struck by a high energy neutron, they undergo this process called nuclear fission or splitting. This splitting process releases a whole bunch of energy all at once, and more neutrons cause a self-sustaining chain reaction. And so in this process of splitting, we have released neutrons, which then go back to split some more. All the while, there's a whole bunch of heat that is being released, as well as other atoms as well. And so this all takes place in a pressurized water nuclear reactor. So here I'll just walk you through the process. We've got in the first step, fuel rods that contain that uranium. They're placed in water in the reactor core. They're also interspersed with neutron absorbing control rods containing boron or cadmium. And so these are the fuel rods here. This is the reactor core. So when the control rods are raised, a chain reaction of nuclear fission or splitting occurs in the fuel rods, and this creates heat. That heat creates high pressure superheated water to flow to a heat exchanger, which generates steam in a secondary loop here. Okay, so the process takes that heat through this primary loop to generate steam, which then gets pumped into a secondary loop, which turns a turbine generating electric power here. And so finally, step 5, the cooling water that has to be pumped in condenses the steam back to water, which returns all the way back to the first step of the heat exchanger. So in this way, the steam is recycled back to be the water that is found in the core reactor here. And all the while, there is electric power that's being generated by the steam that is generated from this splitting reaction. The problem with nuclear power is that we lack safe storage for the waste associated with nuclear power. So there's production of 1,000 tons of uranium fueling the generation of 100,000 tons of tailings and 3.5 million liters of liquid waste. That is a whole lot to contend with. And when we don't have safe storage options, that raises a whole bunch of eyebrows. There are now 200 million tons of radioactive waste in piles laying around in mines and processing plants, and that's only in the United States alone. So how these wastes are managed may ultimately be the overriding obstacle to nuclear power. Right now, the United States has about 77,000 tons of high-level waste. It's considered high level because it's very, very radioactive. So this highly radioactive waste consists mainly of spent fuel rods from commercial nuclear power plants and assorted waste from nuclear weapons production. If you remember to a couple slides ago, many or over half of the US nuclear plants right now are very close to the end of their lifetime, meaning that they're going to have a whole bunch of spent fuel rods that are going to just be laying around because there's no use for them any longer and there's really no safe storage available for them. So in 1987, the US Department of Energy announced plans to build the first high-level waste repository on a barren desert ridge under Yucca Mountain in Nevada. This waste was proposed to be buried deep, deep in the ground, where it was hoped it would remain unexposed to groundwater and earthquakes for thousands of years. And it needs to be undisturbed for that long because the radioactive materials need to decay on their own without potential exposure to humans or wildlife. So funding for this project was ended in 2009. So this project that was going to potentially be the safe storage solution for nuclear waste was ended in 2009, and that was after 20 years of research and about $100 billion in exploratory drilling and investment. Okay, so you can imagine what this means for the future of safe storage of nuclear materials, but we also have to consider what would happen to the residents of this area. So for the foreseeable future, the high-level wastes that were going to go to Yucca Mountain, they're going to be held in large casks in temporary storage facilities located in 39 states across the United States. But the residents living in near these sites fear, of course, as anybody would, that those casks are going to leak. And that means damaging the water as well as the environment, increasing the pollution that they're already contending with. All of this will spell disaster and as well as more dollar signs for those residents and the government. Shifting gears from nuclear power, we also have hydroelectric power. So this is also called water power. And water power was our first industrial power source, believe it or not. Most early American settlements were built where falling water could drive those grist mills and sawmills. And so by the year 1925, falling water generated about 40% of the entire world's electric power. Since then, hydroelectric production capacity has grown about 15-fold, but of course, as we know, fossil fuels have grown and grown in their use much faster than hydroelectric production. So water power is now only 1/4 of the total electrical generation worldwide. What's interesting is that Norway generates about 99% of its power from falling water, even though they have a whole bunch of oil reserves off of their coasts. Other countries like Brazil, New Zealand, Switzerland, they have about 75% of their power being generated from falling water. Canada has 400 hydroelectric power stations, making Canada the world leader in hydroelectric power. What's associated with this power generation? Large dams. These dams, unfortunately, have large impacts. Both large and small dams, they fragment waterways, they destroy biodiversity, and they limit the flow of nutrients and soil. The controversial Belo Monte Dam on the Zizu River, which is located here. This was finished in the year 2015, and it's the third largest dam in the world. It was designed to fuel mining and development in this remote area of tropical rainforest. Unfortunately, of course, it's already shown to be extremely damaging in terms of biodiversity, and it's going to flood about 250 square kilometers or almost 100 square miles of tropical rainforest. The primary purpose was for mining and development, and the indigenous people there have protested that the dam is destroying traditional lands and also will come at the cost of eliminating many endemic species that can't be found on any other habitat on Earth. The unexpected issue that might arise here is associated with methane emissions. This is because the submerged tropical vegetation in the drowned forest will emit methane as it decays. So this is another one of those unintended consequences that we need to find solutions for. There is an alternative. Believe it or not, energy can be generated just through conservation. It's often said that the cheapest form of energy is conservation. Energy reductions are not as visible or exciting as a new power plant or a dam, but they can produce just as much available energy just by avoiding inefficient uses. Conservation can save money as well as reducing our energy footprint all at the same time. So this falls on us to make conscious choices and decisions about our lifestyles and day-to-day energy choices. The simplest probably has to do with light bulb efficiency. And this all comes down to how you calculate energy emissions and consumption. Most of the energy that we consume is actually wasted as heat. High efficiency automobiles are now available, and we also have available to us low emission hybrid gas vehicles or gas electric vehicles that get up to 72 miles per gallon on the highway. We could make choices if we live in an area that's amiable to walking or biking or public transport to take alternative forms of transportation to get around to decrease our energy footprint even more. But oftentimes our budget doesn't allow us to get those high efficiency automobiles or hybrid car or walk or bike everywhere. But what we do have the power over is choosing our light bulbs. So this is just an example of how we can sometimes be really stuck in our ways. An LED bulb, it's called LED, it stands for light emitting diode. It's about $10, okay? A little bit more expensive than your typical incandescent bulb that could be, like $1 at the store. But over years of use, the cheapest bulb, that incandescent bulb, actually costs about 10 times more to operate. Okay, so this has to do with making a little bit of an investment upfront to reap the rewards in terms of reducing your energy footprint, but also it's just more energy efficient and cheaper overall to make that switch from an incandescent bulb to an LED bulb. So here we have the breakdown and the cost effectiveness of efficient technologies, including the LED bulbs here versus your traditional incandescent bulb. So the y-axis is total cost, including the bulb plus the electricity used to fuel the bulb, and the comparison of 1 year, 10 years, and 20 years into the future. So by and large, you can see that the most expensive bulb is that incandescent bulb here, and the cheapest is the LED technology with the two different types of LED bulbs in red and green. Another way that we can make personal choices to decrease our energy footprint is focusing on the home. And this has to do with something called passive housing, or making your home more efficient. This includes no thermal bridges, so materials that can conduct heat through walls, getting rid of those wood or metal components that are good conductors of heat. Not allowing those thermal bridges to exist in your home is a way to have a passive home. Also, making sure that your roof and wall insulation is thick enough to be efficient, making sure that your windows are well sealed as well as your doors during both the summer and the winter, and removing stale air, having your windows be triple pane, which might be a little bit more expensive up front, but overall it will help you reduce your energy costs, and capturing water outside that comes from the sky in rain barrels to capture and use in your garden. And all of that combined, this is kind of what it looks like here in terms of an energy efficient building that can lower costs dramatically for the inhabitant. Let's talk about something called cogeneration. Cogeneration allows you to make electricity from waste heat. So in other words, a resource, that waste heat that would otherwise just go to waste, harnessing that for the generation of electricity. So one of the fastest growing sources of new energy is this process of cogeneration. This allows you to simultaneously produce electricity and get rid of waste products, all within the same plant or the same location. So by producing two kinds of useful energy in the same facility, like electricity and steam or hot water, the net energy yield from the primary fuel is increased substantially from about 30 to 35% to 80 to 90%. So colleges and universities, other large institutions are increasingly installing cogeneration capabilities, as well as cities with district heating. They also use cogeneration. These facilities reduce the load on utilities that help them avoid the expense of building new power plants. The EPA estimates that cogeneration could produce almost 20% of US electrical use, or the equivalent of 400 coal plants. So this is a really promising avenue for energy efficiency in our future. The potential energy from renewables is laid out here in this diagram. What we have on the x-axis are different sources of power, including solar, wind, geothermal, biomass, hydropower, and the ocean. And then on the y-axis, we have energy flow, which is depicted in exajoules per year. So together, all of these sources could supply more than 6 times the current world energy use. So by and large, we do have the capabilities to transition to a renewable source of all of our energy needs on a global scale. And one of those forms is wind power. As mentioned here, wind can meet all of our energy needs if we just develop it in the proper way for wide commercial use. Wind power is the world's fastest growing energy source, and China is the world's largest producer of wind turbines and has the second largest installed wind capacity after Europe. So it's really gaining traction worldwide. And with about 370 gigawatts of globally installed capacity in 2014, it is predicted that 1.5 million megawatts of capacity could be possible by 2020. I'm not entirely sure if we reached that yet, but that was what was predicted for last year. And so wind could meet all of our energy needs. We have the turbines shown here that are located in China, which has the largest installed wind capacity after Europe. This clean technology, meaning that it doesn't give off harmful pollutants into the environment or greenhouse gases, it produces more than 1 million jobs in China, manufacturing equipment for domestic use and import. Okay, so China now has over 63 gigawatts of wind power, or about 1/4 of the world total for wind power. It's increasingly being sought as a source of energy because the prices for wind power have fallen sharply just within the past few years. And it's actually currently the cheapest source of new electrical generation, which costs only about 3 cents per kilowatt hour compared to about 6 cents per kilowatt hour for coal. So not only is it more efficient in terms of bang for your buck, but it's also providing a whole bunch of jobs for the countries that are leaning on this type of energy generation. Here we have a diagram of the wind energy, land consumption, and jobs comparison. So we have in blue land use for coal, photovoltaic, solar thermal, and wind energy. And then in red, we also have jobs for all of those sectors as well. So if you include the land that's required for mining, wind power takes about 1/3 as much area and creates about 5 times as many jobs to create the same amount of electrical energy as coal. Just look at this staggering diagram in comparison here with land use, extremely large for coal generated power. Not so great for wind, but it's still not zero. But just look at the amount of jobs that are generated from wind generated power compared to coal. So that says a whole lot about where we need to be focusing our efforts and infrastructure, especially in the United States right now. An added benefit of wind power is that it provides local control of energy. Cooperatives are springing up everywhere to help landowners and communities finance, build, and operate their own wind generators. This gives them a whole bunch of autonomy in terms of their energy generation. 1 gigawatt of wind power, which is equivalent to one large nuclear or fossil fuel plant, can create more than 3,000 permanent jobs in that area, while paying about $4 million in rent to landowners and $3.6 million in tax payments to local governments. About 20 Native American tribes, for example, have formed a coalition to study wind power. So together, these 20 reservations could generate at least 350 gigawatts of electrical power, which is equivalent to about half of the current total US installed electrical capacity. So really, this option of wind power gives a whole bunch of power back to the people.